Hi, good morning. Sunday morning, I'm still grading. I just wanted to go over the solutions for homework 3. This is Colonel Watts' work. It's not as detailed as what I usually provide you because I have in mind that you're going to be learning and revising things, and I'm perfectly happy to do that. But I think what I'll do is I'll go through her work and then kind of explain to you where everything came from. So here, what she's done is she's listed her random variables. And she hasn't listed her sample space, which I usually ask you to do, and a lot of you are doing that now, but I think these were not probably notes that she meant to have online. But here we go. She has x of x is the number of heads, and y of y is the number of tails. And then she lists out what those possible random variables, the ordered pairs would look like. So you only have 1, 2, 3, 4 ordered pairs. Then you line up the ordered pairs. We did something like this in class, and you literally just calculate the probability directly. And many of you just did this. She's using the multinomial functions, or actually just multiplication rule will do it. So she's got the multiplication rule, and you see these formulas coming out. And I think most people nailed in some way that you would get these non-zero probabilities, but maybe not everything in this table. It was given in a table format. So that's what you needed to do on this problem in a discrete problem, is list out the function completely by table format. In number 2, some of you did try to actually calculate this by hand. It's totally possible to do this. I think there was a couple cadets who did it a couple ways. The easiest way, if there was only 2 here, you would use the binomial function. Since we have 3 here, we're going to use the multinomial, which is actually not in your course objectives. It's 5.9. But you know what? Use your book liberally to look for ways that you can apply some of the things that are a little bit ahead if you need it to. And so here the problem becomes very easy. In your book, if you look in your book, it has something about, so this was used incorrectly by a few of you. And so what I saw in the book, if you read it, they have the formula on page 279. And in page 279, they tell you that the sum of all the random variables, where yi equals the number of trials, is going to be n. So we actually have 2 plus 2 plus 2, which gives you 6. This is why this is going to be a 6 for n. Some of you had 3 for n. You were looking for a quick fix and just plugged in 3 because you thought you had 3 random variables. But you need to read the fine print. There's no easy fix for this class, unfortunately. If there was, if I was teaching 104, I would tell you all the quick fixes. I'm telling you the truth. I never want to make you do more work than you have to. And so you crank this out, and in the formula, you have to identify your P1, P2, and P3 in this case, which turns out to be 1/3, 1/3, 1/3. Your Y1 is 2, your Y2 is 2, and your Y3 is 3. It's a number that you want assigned to an A. So if you define these carefully, you'll have everything in place. I would put more work on this, and so would Colonel Watts. If she was presenting it to you, she would add in where she got every one of the pieces. And she's probably thinking like R here. This is the R code, looks like, that she's written out. All right, so that was the number 2. Number 3, if you drew the picture, and apparently there was a similar problem on Stack Exchange. If you drew the picture, you kind of got almost there. But you're calculating the area of the shaded region. And so once you draw this picture, and you can see what she did is she drew the upper limit of their wait time and their lower limit of their wait time. Again, she's defined her random variables up here, and she's got her uniform function up here, her probability PDF up here. And so she's got her PDF here for the bivariate formulas that she needed. And then she drew out that when this is going to happen, and it turns out you're boxed in by the box of 60 minutes, and you're also boxed in by these lines. And so you're really looking for the shaded area in between. The easiest way I believe to do that is just to calculate area. She has the formula down here. So far, everyone I've graded that's tried to use integrals has got it incorrect. It must be limits of integration. I've asked you to kind of track why that was so. But redoing this as just areas makes it a lot easier. So that was the main error I saw for number 3. And if you did make an error calculating the integrals, I asked you to go back and find this area manually and show where in these integrals it matches up to these areas. Number 4, oh, this problem was so tricky. So I think Nick asked me about this, and I was sleepy one day, and I said, it looks like it's right. But actually, this problem is pretty complicated because your domain for your function is between in the rectangular region 0 to 1 and 0 to 2. And you have a number of cases to think out, actually. One is that you end up inside, your distribution is inside this box. If you're looking, what you're looking for when you write out the distribution function is you're looking for a formula so that if someone asked you what the probability of x1 being less than little x1 and x2 being little x2, no matter what that x1 and x2 is, you should be able to give me in formulaic form what that cumulative probability distribution is, cumulative distribution function is. And so the x1 and x2 could be within this box somewhere. It could be up here, so it's within the range of the interval of x, but not in the interval of y, so it's up here. It could be over here, so it's in the range of the y's, but not the x's. So you have some cases to work out. So if you made an error and just most of you, what I saw was you only integrated this part, this integral right here. And so you have to be extremely careful when you're thinking about this because you really have multiple cases. I gave you a revision to do online. It's under homework, the homework bunch, where you actually have to go in case by case and draw where you are in each region and what it corresponds to. And you'll have different integrals. So it's like a piecewise defined integral in each one of these regions. Please let me know at the end of this. Like, she doesn't have case 1, case 2, case 3, but I think that's maybe a math way to think about it. You have several cases. And so but she does have them listed here. See, x is in the range, but the y is over the range. X is above the range, but the y is within the range. And then the x's and the y's are both out of range. You're going to get a different answer depending on where you are. And so be very careful on these kind that seem like very, very easy. I did tell Nick when he asked me about this problem, like, it seems a little too easy, and she doesn't seem like that type of person. Number 5, the main error I saw here was what these limits of integration were. And we went over it a little bit in class. I think maybe I went to Teams and talked about this and how to find these variations. If you have a revision on this problem, I usually asked you to go back and look at your limits of integration and the limits of integration presented here, or the limits of integration in the book under definitions, and ask why there's a discrepancy. So really review this problem and see why. Like, my biggest error I saw that is that you had something going from 0 to something else. I saw a 0 to k, for example, here, which of course doesn't make sense. You might have thought you're 0 to k here, but your 0 is less than x is less than y, so your upper limit would be actually y here, not k. So review these solutions and see that you match up where they are. Number 6, the biggest error I saw here was knowing what this guy was, because you weren't given this in the problem, but in the problem you were told that it was uniformly distributed over this circle. And if you look at the probability of if it's uniformly distributed, you can actually think of it backwards and say, what would it be if I had to get the mean value to work out the way it should work out in this region? And you will integrate and get, actually it's just the area, right? The area is going to be, it's going to be 1 divided by the, 1/2 divided by the area. So the area of this, it's 1 over the area of this region. So the radius is 2, and it's a circle. And so the area of the circle is 2 pi. And 2 times 2 pi, right? It's pi r squared. So it would be pi times 4. And so that's where you get the 4 pi on the bottom. So that's where your function comes in. And then I kind of talked to you about how to get these limits of integration I think I talked about it online or in class. I don't remember which one. You will probably, I will ask you why she got this as her function and to explain it. And you would go to the uniform distribution section of your book and explain that if you knew that this was the support. So she uses the word support. That is a word that we use quite often. What it means is this is the non-zero region that the function's defined on. If you know that non-zero region, why would this distribution function be 1 over 4 pi? Or 1 over the area. So then it becomes formula crunching, and I don't think there was an issue about formula crunching. It was just what to put in as the function. Number 7, the biggest problem is drawing this region. And drawing this region involves looking at that inequality. And I have you look at it and graph things separately. So you come up with this donut region. Once you have the donut region, people were fine with doing this integration with polar coordinates if they wanted to. I used polar coordinates when I did it. You don't have to. You can just calculate it without that. But where this region comes from, I had you in your notebooks explain to me piece by piece where that region came from. And so you see the answers here. And some of you forgot to actually do part 2. This is actually a really, really important question she's asking you. It was whether they were independent or not. And she explains why they're not independent. And she's quoting theorems from the book. So there's a few homeworks I already looked at where you were searching online for a formula, a fix. There's no fix. There's no quick fix. Look back in your book along these lines and look at the theorems that are relevant to your problem. Number 8 was a tough one. She's laid this out. Xi is the length of demand I. And I asked you to explain why each one of these guys was the way it was if you did not get this problem right. So why was the probability that n is equal to 0 equal to the probability that x1 is greater than 1? Well, that's because if his Twizzler was bigger than length 1, he has nothing to share. And ignore this part. I'm more concerned that you can come up with this formula right here that she's written out. In fact, I would rather have seen this than any Poisson process because this explains why, if you understand what was going on. So I have you lay it out much more in your notebooks, but see if you review this. Definitely review this problem. The final problem she hasn't worked out here, but you would use your definitions inside your book. And I gave some definitions out. I actually sent them out by text. I saw a few very weird formulas coming from the internet, and it was not well done. And I was quite unsure why they would be true. If you used a formula out of the internet, I made you explain where that formula might hold. Go back to the definitions in your book. So there's no use in using a formula outside of class because I will come around to you and ask you where it came from. But I also, I think a message is going to go out from the PD that if you use a formula that was online, you have to prove it verbatim and show why it works before you're allowed to use it in your homework. That's fair game. That's what this class is about. So if you did the work, if you think it's easier actually to prove that formula than to go through your book, then more power to you. I've done those things before, so I think that's perfectly legitimate as long as you can prove it. And this is not done. I think she asked you to have the variance be 1 or something like that and find something, the C's. I did the work, and I think I got something. I don't remember. I think I got something like C equals 1. However, I could be wrong because my memory's bad. All right, so I hope this helps out for your review for the quiz.